In the 1800s, architects faced a hard ceiling. As cities grew, they wanted to build higher, but they were strictly limited by human endurance. No one wanted to climb dozens of flights of stairs every single day. Now, it's true that hoists and cranes have existed for thousands of years, but these ancient lifting devices were strictly used for moving heavy materials. If you put a person on one and the supporting rope snapped, there was nothing stopping the payload from plummeting to the earth. That barrier held until the 1853 New York World's Fair. Inside the massive Crystal Palace, an inventor named Elisha Otis stepped up to prove he had finally solved the safety problem. Otis had himself hoisted high above the crowd on an open platform. Then he ordered his supporting rope to be slashed. The platform only fell a few centimeters. Otis had designed a mechanism using a leaf spring and 2 pivot arms. When the main rope lost its tension, the spring immediately pushed the pivot arms outward, catching into a set of metal teeth on the guide rails and stopping the fall instantly. That single demonstration gave humanity the confidence to build upward. It proved vertical transport was fail-safe, kicking off a 150-year evolution to keep passengers secure as buildings scaled past 100 floors. To understand how we move these cabs, we must look at the 2 main lifting systems. Elevators either push from underneath or they pull from above. This diagram compares the two. On the left, a hydraulic elevator uses oil pumped into a large cylinder to push a piston upward. Because the cylinder must extend deep underground to match the lift's height, this system maxes out at about 6 stories. To reach skyscraper heights, engineers use traction elevators. These lift the massive cab using heavy steel cables pulled by an electric motor high above in a machine room. But deadlifting a massive steel cab filled with people places an enormous, highly inefficient strain on a single overhead motor. The solution to this inefficiency is incredibly simple: the counterweight. This diagram models the physics. The right side counterweight is calibrated to weigh exactly as much as a half-full elevator cab. Because the 2 sides balance each other out over a central pulley, the overhead motor rarely has to lift the entire mass. It only exerts enough energy to tip the balance up or down. Mastering this tension changed the math of vertical transport. Instead of relying on brute force to push a heavy box into the sky, the system operates as an elegant, energy-efficient physics equation. Even with an efficient motor, the ultimate passenger phobia remains the same. What happens if the high-strength steel cables holding the cab somehow completely snap? Modern elevators use between 4 and 8 of these cables, and any single one is strong enough to hold a fully loaded cab. But in the highly unlikely event they all failed, you are protected by the modern descendant of Otis's original invention. This life-saving mechanism is called the overspeed governor. Located high up in the machine room, the governor is attached to its own independent cable. During normal operation, it simply spins safely in tandem with the elevator's routine movements. This schematic shows the internal trigger. If the cab starts accelerating downward too quickly, the governor spins faster. That centrifugal force pushes 2 internal flyweights outward. Once they expand far enough, those flyweights catch onto the stationary gear teeth surrounding them. This abruptly stops the governor's rotation, and the sudden halt yanks its dedicated safety cable tight. That taut secondary cable pulls a lever down at the bottom of the falling cab. This immediate mechanical action deploys 2 heavy-duty emergency clamps that physically bite into the steel guide rails inside the shaft. A catastrophic freefall is completely mechanically impossible. The system is designed so that the very kinetic energy of falling too fast is exactly what powers the brakes to save your life. A falling cab is a highly improbable event in modern times, but there is a much more practical, everyday hazard to consider: keeping a distracted passenger from stepping through an open door and falling into an empty hoistway. To prevent this, elevators use 2 distinct sets of doors. There is a hoistway door permanently built into every floor of the building, and a separate cab door that actually travels up and down with the elevator. This diagram highlights the hoistway door mechanism. Notice that the floor-level doors have no motors of their own. They are permanently locked shut by a mechanical beak interlock, keeping them secured in the downward position. The traveling cab door, however, is equipped with a protruding mechanism called the clutch. As the cab arrives at your floor, this clutch moves into precise alignment with 2 pickup rollers attached to the locked hoistway door. This creates a mechanical handshake. Only when the cab is perfectly aligned does the clutch push against those rollers. This action lifts the locking beak and allows both the cab door and the hoistway door to safely slide open in unison. Because of this strict mechanical logic, the hoistway door will not grant access unless the cab is safely parked right there to catch you. When we step back from these microscopic views of clutches, clamps, and flyweights, we see the impact these machines have had on our surroundings. Elevators allow the ground floor's utility to be replicated dozens or even hundreds of times on a single plot of land. This vertical density is only possible because we removed the historical penalty of climbing the stairs. The modern elevator functions as a habitable robot, managing high-tension cables and mechanical interlocks with minimal human input to ensure constant safety. Stepping into a cab initiates a 150-year-old lineage of mechanical failsafes. Each trip is a result of engineering designed to make the force of gravity a manageable and predictable part of everyday travel.